Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Ohm's Law. Our objective is to take a close look at the cause, effect, and opposition relationship between voltage, current, and resistance, known as Ohm's Law, and use it to calculate unknown quantities given known or observed inputs. Alright folks, this is it. This is the lecture you've been waiting for. Without underestimating its importance, a thorough understanding of Ohm's Law is an absolute necessity for circuit analysis. Try not to screw it up. As vital as this topic is, and as important as I'm making it sound, don't stress, it's easy. If you've been following the series in its intended order, you'll recall I've made numerous allusions to this topic using general concepts and non-numerical examples, hinting at a relationship between cause, effect, and opposition. All this lecture is going to do is make some formal statements about Ohm's Law using electrical terminology and throw some numbers into the picture. You can multiply and divide, can't you? If so, you can do Ohm's Law. Ohm's Law is a simple relationship of cause and effect. On a very basic level, we can state that the effect induced in some system is equal to the cause over opposition. This should make sense. The more effort or cause given to a project or undertaking will undoubtedly yield more effects as long as opposition to your efforts remain low. If, however, opposition increases, the effects will be reduced. Given voltage is synonymous with cause, current synonymous with effect, and resistance synonymous with opposition, we can write this relationship as current equals voltage over resistance. Looking closely at this relationship in either form, we can make the following statements. If opposition was held constant and cause increased, effects should increase. Stated another way, same resistance, more voltage yields more current. Conversely, if opposition was held constant and cause decreased, effects should decrease. Stated another way, same resistance, less voltage yields less current. Other observations are equally as valid. If cause was held constant and opposition increased, effects should decrease. Stated another way, same voltage, more resistance yields less current. Conversely, if cause was held constant and opposition decreased, effects should increase. Stated another way, same voltage, less resistance yields more current. One can express Ohm's Law graphically using a three-variable pyramid with voltage in units of volts at the apex, and current in units of amps, and resistance in units of ohms side by side forming the base. Using the shorthand representation for voltage, current, and resistance, we can write the triangle as V over IR. To solve for current in unit of amps, take voltage in units of volts and divide it by resistance in units of ohms, because voltage is over resistance. To solve for voltage in units of volts, take current in units of amps and multiply it times resistance in units of ohms because they're side by side. Finally, to solve for resistance in units of ohms, take voltage in units of volts and divide it by current in units of amps because voltage is over resistance. Before we attempt some illustrated example problems of Ohm's Law, we need to discuss some important topics. Specifically, we need to introduce polarity markers and subscript and nodal notation. Additionally, we need to differentiate between a voltage rise and a voltage drop. These topics might seem a little unnecessary at this point, and even glaringly obvious given such simple circuits, but trust me, this brief orientation will make life much easier as we progress into more complicated circuits. It's hard to talk about these topics independently without bringing all of them into play, so we're kind of going to talk about them all together. You may find it necessary to rewind once or twice if you don't understand all the contents in this section for the first time through. Consider this simple electrical circuit formed by a single voltage source E and a single variable resistor R1. Let's say the variable resistor R1 is currently set to a value of 60 ohms. First, realize an electrical circuit exists via resistor 1. Conventional current leaves the positive terminal of the voltage source and travels through resistor R1 top to bottom, then returns to the negative terminal of the voltage source. Let's designate current through resistor R1 as I1. Second, the voltage source E and resistor R1 contact each other at nodes, where a node is a point of common connection for two or more elements. Customarily, I indicate nodes using letters. Let's call the top node A and the bottom node B. Nodes, again, are common points of connection. Let's now differentiate between active and passive elements in electrical circuits and discuss how to differentiate between and annotate voltage rises and voltage drops. A voltage source is an active element that establishes a voltage differential across its terminals. The polarity markers on a voltage source indicate the terminal with a positive polarity marker is higher with reference to the terminal with a negative polarity marker. Active elements, like voltage sources, supply energy to electrical circuits. A voltage source, if you want to think of it this way, is like a ladder that grabs handful after handful of charges, lifts them up, and repeatedly lets them fall down a circuit like a slide. An example of a DC voltage source might be a battery, which converts stored chemical energy to electrical energy. A DC generator, which converts mechanical energy to electrical energy. A PV solar panel, which converts radiant energy to electrical energy. Or a power supply, which converts commonly available AC electrical energy to DC electrical energy. The point being, active elements induce a voltage rise from some other external source of energy, and they supply electrical energy to a circuit. I customarily indicate a voltage source or a rise using the shorthand E, which stands for electromotive force. Depending upon your country of origin, this is synonymous with voltage. If there is more than one source, I'll differentiate between sources by adding a subscript, as in E1 or E2. When measuring the voltage rise induced by an active element, like a voltage source, a voltmeter is customarily employed such that the black reference or common lead is on the negative polarity marker and the red lead is on the positive polarity marker. Let's say the single source in the circuit, E, induces a voltage rise of 12 volts. A voltmeter configured in this fashion would read 12 volts. Now let's examine passive elements. Passive elements, like resistors, are those elements in a circuit down which current slides. Any voltage rise induced by the source is dropped by all elements within the circuit. In summary, what goes up must come down. Passive elements convert electrical energy into some other form of energy. Resistors convert all supplied electrical energy to heat. Voltage drops also have a polarity indicated using a plus and a minus. The point with a positive polarity marker is higher than the point with a negative polarity marker. In the case of a simple circuit with a single element, it may or may not seem painfully obvious that every voltage rise is accompanied by an equal and opposite voltage drop. Thus, the single element in this circuit will have a voltage drop equal in magnitude to that supplied by the source. When measuring voltage drops across passive elements, a voltmeter is customarily employed such that the reference or common lead is on the negative polarity marker or downstream end of conventional current, and the red lead is on the positive polarity marker or upstream end of conventional current. A voltmeter configured in this fashion will read a voltage drop of 12 volts. I customarily annotate voltage drops using the shorthand V. If there is more than one voltage drop, I'll differentiate between them using two, technically three methods. One making use of single subscript notation, the other making use of double subscript notation, and the final method also making use of a single subscript, although employing a common reference. In all scenarios, I must remind you that voltage is a two-point measurement. Using single subscript notation, I could call the voltage drop across resistor R1 V1, implying that it is the voltage drop across the two terminals of resistor 1. Using double subscript notation, I could also call the voltage drop across resistor R1 VAB, implying that it is the voltage drop from node A to node B, which happens to be the nodes which touch the two terminals of resistor 1. Finally, if we formally declare some node to be a reference node, meaning it is the point from which all other points are measured, we can use a modified form of double subscript notation by ditching the standard reference node and using only a single subscript. For example, if we formally declare node B to be the reference node, we can call the voltage drop across resistor 1 VA, with the understanding that VA means voltage at A with reference to the assumed point of reference B. Regardless of the notation method employed, it's helpful to remind ourselves that active elements like voltage sources convert energy from some external source into electrical energy, whereas passive elements like resistors convert supplied electrical energy in the circuit to some other form of energy, in the case of a resistor, heat. Active elements like sources are associated with voltage rises, whereas passive elements like resistors are associated with voltage drops. Importantly, you will note that conventional current leaves an active source's positive terminal and enters its negative terminal. Conversely, conventional current enters a passive element's positive terminal and leaves its negative terminal. I say again, you will note conventional current leaves an active element positive terminal and enters its negative terminal, whereas conventional current enters a passive element's positive terminal and leaves its negative terminal. Again, the subtleties of these different styles of notation may escape your notice using such simple circuits. However, using these standards, we can identify and differentiate between numerous different electrical properties within a more complicated circuit. For example, consider the more complicated series parallel circuit consisting of 3 resistors, R1, R2, and R3 arranged in the following fashion. Voltage source E is between nodes A and C. Resistor R1 is between nodes A and B. Resistor R2 is between nodes B and C. And finally, resistor R3 is also between nodes B and C. Conventional current would travel through the circuit in the following manner. Source current leaves the positive terminal of the voltage source, enters the top of R1, travels through R1, leaves the bottom of R1, and enters node B. Here, current splits into 2 different paths. A portion of current enters the top of R2, travels through R2, leaves the bottom of R2, and enters node C. The other portion of current leaving node B enters the top of R3, travels through R3, leaves the bottom of R3, and enters node C. At node C, current recombines and enters the negative terminal of the voltage source. We could call the current traveling through R1 I1, the current traveling through R2 I2, and the current traveling through R3 I3. Given resistors are passive elements, we would assign the following polarity markers based on the direction of conventional current travel. Conventional current enters the top of R1 and leaves the bottom, so the polarity markers would be assigned positive to negative, top to bottom. Similarly, current enters the top of R2 and leaves the bottom, so the polarity markers would be assigned positive to negative, top to bottom. Finally, current enters the top of R3 and leaves the bottom, so the polarity markers would also be assigned positive to negative, top to bottom. Using single subscript notation, the voltage drop across R1 could be designated as V1, the voltage drop across resistor 2 designated as V2, and the voltage drop across resistor 3 designated as V3. If, however, we chose to use double subscript notation, the voltage drop across resistor R1 could be designated as VAB. The voltage drop across resistor R2 could be designated as VBC, and the voltage drop across resistor R3 could also be designated as VBC. Finally, if we were to formally declare node C to be the reference, we could designate the voltage drop across resistor R2 as VB, as well as the voltage drop across resistor R3 as VB, where the unstated node C is assumed to be the reference. Using this same standard, the voltage drop across resistor R1 could be designated as VA minus VB, where again the unstated node C is assumed to be the reference for both voltages. If I was to use double subscript notation, VA with respect to C minus VB with respect to C would equal VAB. Again, this may seem confusing at first, but trust me, these standard methods will make the examination of later more complicated series, parallel, and series parallel circuits that much easier. We'll revisit these subtleties in later lectures. Returning to our simple circuit, the voltage drop across resistor R1 could be designated as V1 as well as VAB, or if we were to formally declare node B as reference from which all their points to be measured as VA. Regardless, given a 12-volt rise induced by the source, all 12 volts will be dropped across the single resistor R1. Let's use Ohm's law to determine the anticipated amount of current flow in this circuit. Recall that current is the flow of charges through a conductive path with a voltage differential across that path. For a given voltage, if a path has low resistance, current will be high. Conversely, if a path has a high resistance, current will be low. Given we know the voltage across a known resistor, we can use Ohm's law to calculate the current through it. Current is equal to voltage over resistance. An application of Ohm's law demonstrates 12 volts over 60 ohms yields an anticipated current draw of 0.2 amps or 200 milliamperes. If we needed to experimentally measure current through this circuit, it would necessitate us incorporating an ammeter in series to allow a single point flow measurement somewhere in the circuit. This would necessitate us breaking the circuit and installing an ammeter in line or in series with the element through which we wish to measure current. There's a couple places we could insert an ammeter. First, we create a series circuit where current leaving the positive terminal of the voltage source enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the top of resistor R1, travels through resistor R1, leaves the bottom of resistor R1, and returns to the negative terminal of the voltage source. You'll note the inclusion of the ammeter in series necessitates the introduction of an additional accessory node, or point of common connection I'm calling a single prime. The only elements connected to node A are the power supply positive terminal and the ammeter indoor. The only elements connected to node A single prime are the ammeter outdoor and the top of resistor R1. Finally, the only elements connected to node B are the bottom of resistor R1 and the power supply negative terminal. One and only one path exists for current, such that the ammeter is a single point flow rate measurement. An ammeter configured in this fashion would measure 200 milliamperes. This is one way of configuring an ammeter to measure current through resistor R1. Here's another way of measuring current through resistor R1. Given 200 milliamperes of current flows through all elements in this simple circuit, any single point measurement anywhere in the circuit would suffice. In this configuration, current leaves the positive terminal of the voltage source, enters the top of resistor R1, travels through resistor R1, leaves the bottom of resistor R1, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, and returns to the negative terminal of the voltage source. As previously, you'll note the inclusion of the ammeter in series necessitates the introduction of an additional accessory node or point of common connection. In this case, I'm calling node B single prime. The only elements connected to node A are the power supply positive terminal and the top of resistor R1. The only elements connected to node B are the bottom of resistor R1 and the ammeter indoor. Finally, the only elements connected to node B single prime are the ammeter outdoor and the power supply negative terminal. One and only one path for current exists, such that the ammeter is a single point flow rate measurement. An ammeter configured in this fashion would also measure 200 milliamperes. Let's use this simple circuit as a basis of comparison to demonstrate simple manipulations of Ohm's law. Again, given 12 volts across a variable resistor currently set at 60 ohms, we should anticipate a current reading of 200 milliamperes. Given resistor R1 is variable, let's say I adjust resistor R1 to some unknown value. In the process, we observe current to go up to 300 milliamperes. What did I do? Did I increase or decrease resistance? Think about it. No numbers, just think about it. Voltage stayed the same and current increased. Did resistance or opposition to current flow go up, go down, or remain the same? If you're tracking, you should realize that resistance has decreased. A simple Ohm's law calculation supports this assessment. Resistance is voltage over current. An application of Ohm's law demonstrates 12 volts over 300 milliamperes yields an anticipated resistance of 40 ohms. Resistance did indeed go down. Let's try another manipulation of Ohm's law using the same circuit in its present configuration. Variable resistor R1 remains set at 40 ohms. However, let's say I adjust the voltage supply to some unknown value, and in the process we observe current to go up to 400 milliamperes. What did I do? Did I increase or decrease voltage? Think about it. No numbers, just think about it. Resistance stayed the same and current increased. Did voltage go up, go down, or remain the same? If you're tracking, you should realize that voltage must have increased. A simple Ohm's law calculation supports this assessment. Voltage is current times resistance. An application of Ohm's law demonstrates 400 milliamperes times 40 ohms yields an anticipated voltage of 16 volts. Voltage did indeed go up. For this simple circuit, we would anticipate the source to impart a 16 volt rise to the circuit, as well as resistor R1 to experience a 16 volt drop. Before we move on, try this set of example problems on for size. Given known quantities in each scenario, use Ohm's law to calculate the unknown quantity. For the first problem, we have a known voltage drop and a known resistance and are being asked to solve for current. For the second circuit, we have a known current, a resistor color code, and are being asked to solve for the voltage drop. Finally, for the third circuit, we have a known current, a known voltage drop, and are being asked to solve for the resistance. By all means, pause the lecture and try this on your own. Do not just sit there and wait for me to guide you through these illustrated example problems. Pause the lecture, take out your paper, pencil, and scientific calculator and take your best shot. Express all answers using proper engineering format to the 10th place. If you're tracking, you should have obtained the following results. Our first problem features a 270 ohm resistor experiencing a 48 volt drop across it, and we're being asked to solve for current through it. Current is voltage over resistance. 48 volts over 270 ohms yields 177.8 milliamperes of current. Given the polarity markers for this passive element, we would expect conventional current to travel top to bottom. Our next problem features a resistor with a color code of green, blue, brown, gold, experiencing 26 milliamps of current traveling top to bottom. We're being asked to solve for the voltage drop across it. A color code of green, blue, brown means 5, 6 with 1, 0, or 560 ohms. Voltage is current times resistance. An application of Ohm's Law demonstrates 26 milliamperes times 560 ohms demonstrates this resistor must be experiencing a 14.6 voltage drop. Given the direction of conventional current travel, the voltage drop polarity would be oriented positive to negative, top to bottom. Finally, our last problem features an unknown resistor experiencing a 9.9 volt drop across it and 45 milliamperes of current traveling through it. We're being asked to solve for resistance. Resistance is voltage over current. 9.9 volts over 45 milliamperes yields 220 ohms of resistance. You note conventional current flow travels positive to negative, top to bottom, as one would expect for a passive element. Alright, hopefully that first set wasn't too hard. Here's the second set of Ohm's Law example problems with the intent of illustrating the relationship of cause, effect, and opposition. Given known voltage and resistance in each scenario, use Ohm's Law to calculate the unknown current. Express all answers using proper engineering format to the tens place. Be on the lookout for interesting results. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Our first problem features a 48 ohm resistor experiencing a 12 volt drop across it. We're being asked to solve for current through it. Current is voltage over resistance. An application of Ohm's Law demonstrates 12 volts over 48 ohms yields 250 milliamperes of current. Let's use the results of this first problem as a basis of comparison for the remaining problems. Our second problem also features a 48 ohm resistor, only this time it's experiencing a much smaller 2 volt drop across it. We're being asked to solve for current through it. Current is voltage over resistance. An application of Ohm's Law demonstrates 2 volts over 48 ohms yields 41.7 milliamperes of current. Although we're employing the same resistance, this circuit experiences substantially smaller current because the voltage differential across it is much smaller. Our third problem also features a 48 ohm resistor, only this time it's experiencing a much larger 72 volt drop across it. We're being asked to solve for current through it. Current is voltage over resistance. Ohm's Law demonstrates 72 volts over 48 ohms yields 1.5 amps of current. Although we are employing the same resistance, this circuit experiences substantially larger current through it because the voltage differential across it is greater. It makes sense. These two examples are intended to illustrate a basic fact. Given constant resistance, less voltage yields less current, and more voltage yields more current. Our fourth problem also features a 12 volt source. Only this time it's experiencing much less opposition in the form of a 4 ohm resistor. We're being asked to solve for current through it. Current is voltage over resistance. Ohm's Law demonstrates 12 volts over 4 ohms of resistance yields 3 amps of current. Although we're still using a 12 volt source, this circuit experiences substantially larger current through it than our first one because the source sees much less opposition. Finally, the fifth problem also features a 12 volt source. Only this time it's experiencing much more opposition in the form of a 1.2 kilo ohm resistor. We're being asked to solve for current through it. Current is voltage over resistance. Ohm's Law demonstrates 12 volts over 1.2 kilo ohms yields 10 milliamperes of current. Although we're still using a 12 volt source, this circuit experiences substantially smaller current through it than our first one because the source sees much more opposition. It makes sense. These two last examples were intended to illustrate a basic fact. Given constant voltage, less resistance yields more current, and more resistance yields less current. The punchline for this entire set of example problems is this. Ohm's Law is a linear property. Given constant resistance, every increase in voltage results in a proportional increase in current. To demonstrate the linearity of Ohm's Law, let's plot current as a function of voltage for this set of resistors, R1 having a value of 240 ohms and R2 having a value of 390 ohms. Let's look at the 240 ohm resistor. Consider a 240 ohm resistor that experiences 0 volts to 24 volt differentials in 2 volt increments. With a 0 volt differential across it, no current will flow through it. If we step voltage up to 2 volts, Ohm's law demonstrates we should anticipate 8.3 milliamperes of current to flow through it. If we step voltage up to 4 volts, Ohm's law demonstrates we should anticipate 16.7 milliamperes of current to flow through it. If we perform these same Ohm's law calculations in 2 volt increments, we should observe every increase in voltage to result in a proportionate increase in current. Note how the current at 4 volts is twice that observed at 2 volts. If we double voltage from 4 volts to 8 volts, the current at 8 volts is twice that observed at 4 volts. If we triple the voltage from 8 volts to 24 volts, the current at 24 volts is 3 times that observed at 8 volts. In short, Ohm's law is a linear property, and when current as a function of voltage is plotted, the results speak for itself. Given constant resistance, every increase in voltage results in a proportionate increase in current. As an exercise with the viewer, I invite you to calculate current through the 390 ohm resistor at the same specified voltages. Once you've got this data, go ahead and plot current as a function of voltage for the 390 ohm resistor on the same scale and the same plot we utilize for the 240 ohm resistor. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. As previously, for every increase in voltage, we observe a proportional increase in current. Current at 12 volts is twice that it observed at 6 volts. Similarly, current at 12 volts is 3 times that observed at 4 volts. In short, Ohm's law is again linear. When plotted, the difference between current as a function of voltage for the two resistors is the rate of change or slope, which is an understandable reflection of the differing resistance values. For each operating condition, the larger 390 ohm resistor experiences less current, and the smaller 240 ohm resistor experiences more. As a result, the slope of current as a function of voltage for the smaller 240 ohm resistor appears steeper, whereas the larger 390 ohm resistor less so. These simple plots are graphical evidence of the basic facts we discussed earlier. First, given constant resistance, less voltage yields less current, and more voltage yields more current. At 8 volts, current through the 240 ohm resistor is 33.3 milliamperes, whereas at 16 volts, current is 66.7 milliamperes. Similarly, at 8 volts, current through the 390 ohm resistor is 20.5 milliamperes, whereas at 16 volts, current is 41 milliamperes. Second, given constant voltage, more resistance yields less current, and less resistance yields more current. At 8 volts, current through the 240 ohm resistor is 33.3 milliamperes, whereas at the same 8 volts, current through the larger 390 ohm resistor is only 20.5 milliamperes. Similarly, at 16 volts, current through the 240 ohm resistor is 66.7 milliamperes, whereas at the same 16 volts, current through the larger 390 ohm resistor is only 41 milliamperes. The nature of these plots and the conclusions drawn from these plots should be understandable, and if not, I'm asking that you pause the lecture and stare at them without blinking until you do understand them on every level that I'm asking you to. Moving on. Lest you think Ohm's law is limited in application to the simplest of circuits, let me remind you that Ohm's law is the most fundamental of all electrical properties and can be applied in many circumstances, including series circuits, parallel circuits, and more complex series parallel circuits. Given Ohm's law has a relationship of 3 properties, current, voltage, and resistance, we can apply Ohm's law anywhere we know 2 properties and wish to solve for the third. As a preview of Ohm's law applications for more complicated circuits, consider the series parallel circuit consisting of 3 resistors, R1, R2, and R3 arranged in the following fashion. Voltage source E, having a value of 24 volts, is between nodes A and C. Resistor R1, having a value of 40 ohms, is between node A and B. Resistor R2, having a value of 100 ohms, is between node B and C. And finally, resistor R3, having a value of 400 ohms, is also between node B and C. Let's say the only additional piece of data we have about this circuit is a single voltage reading, VBC, known to be 16 volts. Given both resistor 2 and resistor 3 are between node B and C, we now know that both voltage across resistor 2, V2, and the voltage across resistor 3, V3, to also be 16 volts. Let's apply Ohm's law to see if we can solve for other unknown circuit properties. Consider resistor R2 from node B to C. We know resistance and we know voltage. Current is equal to voltage over resistance. An application of Ohm's law demonstrates current through resistor 2, I2, is 160 milliamperes. Consider resistor 3, also from node B to C. We know resistance and we know voltage. Current is equal to voltage over resistance. An application of Ohm's law demonstrates current through resistor 3 is 40 milliamperes. You'll note the parallel elements, resistor R2 and R3, experience the same voltage differential. However, more current travels through the lower resistance path offered by R2, and less current travels through the higher resistance path offered by R3. It makes sense. Same voltage, less resistance yields more current. Conversely, same voltage, more resistance yields less current. Take a look at what's happening at node B. 160 milliamperes of current leaves node B and travels to C through resistor R2. Similarly, 40 milliamperes of current leaves node B and travels to node C through resistor R3. It stands to conjecture 160 milliamperes plus 40 milliamperes, or 200 milliamperes, must therefore be entering node B through resistor R1. This is a preview of Kirchhoff's current law, which states the summation of currents entering a node equals the summation of currents leaving a node. We'll examine Kirchhoff's current law in greater detail in later lectures on fundamental parallel circuit properties. In short, what goes in must come out. Through this application of Kirchhoff's current law, we now have an additional data point concerning resistor R1. We now know the current through resistor R1, I1, must be 200 milliamperes. We know current and we know resistance. Voltage is equal to current times resistance. An application of Ohm's law demonstrates voltage across resistor R1, V1, or for that matter VAB, to be equal to 8 volts. You'll note the summation of VAB plus VBC, 8 plus 16, equals 24 volts, or the voltage from A with respect to C. This is a preview of Kirchhoff's voltage law, which states that for any closed loop, the summation of voltage rises equals the summation of voltage drops. We'll examine Kirchhoff's voltage law in greater detail in later lectures on fundamental series circuit properties. In short, what goes up must come down. Although I did employ more advanced applications of Kirchhoff's current law and Kirchhoff's voltage law, topics we'll examine in later lectures, you'll note that each application of Ohm's law, the topic of this particular lecture, for each of the 3 resistors, can be considered an isolated event. We're given 2 known properties. Ohm's law can be used to solve for the unknown third property. As we introduce progressively more and more challenging circuit analysis scenarios, you'll find yourself continuously employing Ohm's law, and we'll be glad for all the practice you did today. Alright, before we bring this lecture to a close, let's talk about using Ohm's law to troubleshoot electrical systems. Troubleshooting is the systematic identification of a problem exhibited by a system and the subsequent correction. This is $1 million buzzword for aspiring technicians. Everybody wants to be a troubleshooter. There exists a population of hucksters out there that try to sell troubleshooting as a separate skill, only tangentially related to basic electrical properties, but they are all charlatans, frauds, and swindlers. Anything packaged and sold as troubleshooting without incorporating a thorough understanding of basic electrical properties is mere button pushing, totally inapplicable to real-world problems where what can go wrong often does. If you're enrolled in a hardware lab that accompanies a basic electronics course, you are troubleshooting, even if it doesn't say troubleshooting lab in the course description. I know it's frustrating when your instructor says, build me this, show me that, and walks away, and it takes you 2 or 3 or even 4 attempts to get it right. But guess what? All the time you spend finding and fixing mistakes isn't wasted. It's being spent developing troubleshooting skills. That's the point of a hardware lab. Get inside one and make mistakes in a safe and supportive learning environment. Make as many mistakes as you can and make them early and make them often. Make all the mistakes. Get all of the mistakes out of the way up front. Here's the tricky part though. Be sufficiently aware enough to prevent their reoccurrence. Recognize the clues that led you to discovering the mistakes, learn from your mistakes, and never repeat them. Troubleshooting is not a skill separate from basic electrical knowledge. At its most essential level, troubleshooting is the systematic application of basic electrical properties. Think of the term law. Ordinarily, we think of laws as things you get sent to jail for or pay a fine if you violate them. Ohm's Law is not that type of law. There's no Ohm's Law jail if you violate it, and you can't pay some lawyer to twist the wording of Ohm's Law to make your circuit work like you want to. Ohm's Law is a law like gravity, and that it goes to work every second of every day and cannot be violated. Reality always obeys Ohm's Law, and it's your job as a troubleshooter to interpret reality. Say, for example, you're tasked with troubleshooting a system that habitually trips an overcurrent protection device, or, lacking overcurrent protection, has an annoying tendency to burst into flames. Fire is a pretty good indication that the ampacity or current carrying capability of this device has been exceeded. Even if you have never seen the system before, nor even have the remotest idea what it does, as an effective troubleshooter understanding Ohm's Law, you are aware of two possible causes for this problem. If the current is too high, either the voltage is too high, or the resistance is too low, or maybe both. There are simply no other possible explanations for this occurrence. You don't need a $50 flowchart to tell you this, and it's not like Ohm's Law is some magic secret. At its heart, your understanding of Ohm's Law quickly and efficiently cuts out a whole lot of dead ends and useless busy work. Determining why the voltage is too high, why the resistance is too low, or both is the next step in troubleshooting. This is where an intimate understanding of how a system is intended to operate comes into play. It is my intention not to roll out a flowchart that shows you how to troubleshoot a single system, but rather arm you with sufficient technical knowledge to understand and thus troubleshoot any system. This is not some paint-by-numbers, quick and easy scheme where you can send some dude in the back of a comic book $50 and he'll send you a black belt in Kung Fu. I'm going to tell you right now, this is going to be a long, hard, and grueling road full of bruises, sore backs, hurt feelings, and crushed expectations. You need to have the strength of character to recognize that all this hard work will be worth it in the long run. The point is, a skill like Ohm's Law is a basic principle, equivalent to learning how to throw a decent punch if you're training for a fight, and it needs to be practiced, drilled, and developed over and over until it becomes an automatic response necessitating little cognitive resources. That's the purpose of study. It's hard and exhausting for a reason. You're developing important skills that need to become habits, and the only way to do so is through repetition and practice. Regarding good work practices, you simply must perform the calculations first. That way you know what to expect. Make sure you use the correct components. Make sure you connect them in the correct manner. Make sure you supply them with a proper level of voltage, and make sure you take measurements in the right place. In short, imagine how well lab will go if you know what you're doing. Don't just randomly pull wires, push buttons, and hope it works out okay. In this spirit, here's a couple simple troubleshooting scenarios that will test your basic understanding of Ohm's Law. As basic and contrived as these scenarios might be, don't for a moment underestimate the importance of Ohm's Law. Trust me, you'll find ample opportunities to employ Ohm's Law in more complicated troubleshooting scenarios. Let's say we're tasked with building this simple circuit where a 20-volt source is supplying current to a 1 kilo-ohm resistor. Do the calculations first. What's the current you would expect flowing through this circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Current is voltage over resistance. An application of Ohm's Law demonstrates we should anticipate 20 milliamperes of current. Let's say we build this circuit, and as soon as we turn on the power supply, current spikes to 200 milliamperes, and rather quickly, the resistor's paint job turns an ugly shade of brown, starts smoking, and is soon engulfed in flames. What's the problem? The answer is right in front of you if you know where to look. There's really only three elements in this simple circuit: the voltage source, the ammeter, and the resistor, so it's obviously one of these that are at fault. Let's say a quick check of the voltage source with your voltmeter indicates the source really is at 20 volts. What's the problem? It's your lab partner. I warned you about this, didn't I? Instead of grabbing a 1 kilo-ohm resistor with a brown, black, red, gold 4-band color code, i.e. 1 0 with 2 zeros, they grabbed one with a brown, black, brown, gold 4-band color code, i.e. 1 0 with 1 0 or 100 ohms. Pay attention to the third band. Didn't I say that before too? Pay attention to your lab partner. Never trust them. A 100 ohm resistor provides substantially less opposition. 900 ohms less to be exact than the specified 1 kilo ohm resistor. The application of Ohm's law demonstrates that the smaller 100 ohm resistor with a 20 volt differential across it should experience 200 milliamperes of current, i.e. 10 times greater than what we anticipated. No wonder it burst into flames. Ohm's law says current will be high for low resistance paths. Tying this troubleshooting example to the development of good lab practices, had you taken the time to measure the resistance with an ohm meter, or at the very least interpreted the 4-band resistor color code prior to turning on the power, this whole sordid tale would never have happened. Your lab partner isn't just there to make you look good. They're there to dummy check your work. And believe me, you are there to double and triple dummy check their dumb work. Here's another very simple troubleshooting example necessitating your understanding of Ohm's law. Let's again use a 20 volt source and a 1 kilo ohm resistor. This time it really is 1 kilo ohm because no way are you going to fall for that one ever again. Let's say you observe no voltage drop across the 1 kilo ohm resistor, nor do you observe any current. What's the problem? If there is no voltage drop across the resistor, it means there is no current through it. Ohm's law says so. Voltage equals current times resistance. 0 amps times 1 kilo ohm is 0 volts. First, ask yourself, did you turn the source on? You'd be surprised how many troubleshooting scenarios are resolved simply by pressing the large button that says on. I've done this myself more than I'd like to admit. What if the source was on, and you still observe no voltage drop across the resistor, nor any current through it? Ask yourself, what is stopping current? Perhaps something with an infinite resistance. I previously assured you that it was in fact a 1 kilo ohm resistor. However, are it and the ammeter the only elements in the circuit with this source, or is there something else in series with it? Think about what I'm asking. What is something with an infinite resistance? Something with an infinite resistance is an open or an incomplete circuit. This is where intimate knowledge of your circuit building environment, typically a protoboard in lab, comes into play. You may have the correct voltage and you may have the correct resistor, but a complete circuit may not exist because of an inadvertent open. A complete circuit, including an ammeter, looks something like this. Current leaves the positive terminal of the voltage source, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the top of resistor R1, travels through resistor R1, leaves the bottom of resistor R1, and returns to the negative terminal of the voltage source. An open anywhere in this path would prevent completion of the circuit and disrupt all current flow. Consider an open between the voltage source positive terminal and the ammeter indoor. Current won't flow because no circuit exists. Another possibility for an open exists between the ammeter outdoor and the resistor. Current again won't flow because no circuit exists. Another possibility for an open exists between the bottom of the resistor and the negative terminal of the voltage source. Current again won't flow because no circuit exists. Finally, consider the test leads in the ammeter itself. Instruments like ammeters often include internal fuses to protect the device from high currents. In the event of a ruptured fuse, the ammeter itself prevents completion of the circuit and thus no current flows. Additionally, consider the consequence of damaged test leads or test leads that are not properly inserted that prevent completion of the circuit. In summary, if you observe no current flow, you are definitely dealing with an open. Having determined an open as the source of your problems, it's now up to you to find it. Oftentimes, one needn't resort to instrumentation to find the source of the problem. Just look at it. You might find a wire dangling out into empty space, or a component or wire misplaced or landed on the wrong spot. Attention to detail in viewing the circuit from several different angles might reveal the cause for the missed connection. As some general advice to aspiring technicians, I will be so bold to proclaim that fully 99% of all electrical problems you will ever encounter in the field are the result of open circuits. Either some wire wasn't properly tightened on a screw terminal, or it was properly tightened and shook loose, got pulled out, or got cut. Last but not least, do not rule out the possibility of improper use of instrumentation being the source of your problem. This caution is especially relevant when your lab partner is behind the wheel. If one is employing a voltmeter incorrectly, one will not be able to properly measure voltage. Similarly, if one is employing an ammeter incorrectly, one will not be able to properly measure current. We'll examine the proper application of voltmeters and ammeters in later lectures. In closing, realize there is no way one can possibly foresee and anticipate all possible sources of problems within a system, and anyone who says so is a liar. I am not saying that technicians accustomed to troubleshooting by the book or using some company-established procedures cannot resolve errors, but I am saying that a flexible technician with knowledge of basic electrical properties like Ohm's Law can resolve errors that aren't even in the book. Before we wrap up, here's a consolidated list of some of the general troubleshooting advice we discussed today. Again, this advice cannot possibly cover all possible scenarios, but in my opinion, it is sufficiently general enough to encompass some basic principles of troubleshooting for your first couple DC circuit labs. Open circuits mean infinite resistance and result in no current. Short circuits, in contrast, mean low resistance and result in high current. If you can walk away from this lecture understanding just these two simple facts, I will consider my efforts having not gone in vain. If you can't remember both, remember this one. Open circuits do not allow current to flow. If you turned all possible troubleshooting scenarios into animals, where their population is representative of their frequency of occurrence, the open circuit is like a beetle, which even if you combined all other species on Earth, would still outnumber them like 1,000,000 to 1. Your first error is your dubious choice of lab partners. Your next 999 errors are going to be open circuits. Do the calculations first. Know what to expect. Do not bring a dull knife to a gunfight. By doing the calculations up front, you'll have a basis of comparison if your observations match your expectations or if they are wildly wrong. Double check your components. Make sure you're using the right components and install them correctly. Read the values on the side. If you can't read the value, use an ohm meter to measure and verify the specified value. Check to see if a switch works before you put it in a circuit. Resistance of a closed switch should be close to 0 ohms, whereas the resistance of an open switch should be infinite. Test everything because lab equipment gets hammered by generation after generation of students. Sometimes out of sheer exhaustion, components, test leads, or meters just die. Double check the circuit. Make sure it's hooked up as intended. Use colored wires and label the nodes. Look at anything you suspect of being open from all angles, not just the top. Different viewpoints often quickly reveal a missed or off by one connection. Supply your circuit with the correct voltage. Verify output voltage before and after you hook it up to your circuit. Use your DMM to check it. If you're going to use your DMM, use it properly. We already covered the ohm meter in a previous lecture. We'll go into details about voltmeters and ammeters real soon, but recall the basics. Use the checklist. I am not urging you to use this checklist every time. I am demanding you use this checklist every time. The use of this checklist will save your measurement equipment and circuit a lot of costly downtime and may potentially save your life. I am not overstating the benefits of using this checklist. Use the checklist. Think about it. Really think about it. Take your time and think before you act. The checklist has 4 steps. Follow them 1 through 4, and you will get it right every single time. Skip a step, do a step wrong, or do a step out of order, and you will get it wrong every single time. Function. Choose the quantity you want to measure: voltage, current, or resistance. DMMs use different detection mechanisms to measure different quantities, and if your DMM is in the wrong mode, it won't work. Leads. Put your leads in the correct place. For voltmeter and ohm meter mode, the leads go in one place, and in ammeter mode, they go in a different place. Of note, customarily the red plug goes into a red hole, and the black plug goes into a black hole. You would be surprised how many people mess this up under stress. Range. If your DMM is not auto-ranging, one must manually choose an appropriate range to obtain the most accurate measurement results. Whereas if your DMM is auto-ranging, your DMM will automatically pick the most appropriate range to obtain the most accurate measurement results. Related to range, be aware there is a limited range a meter and you can safely measure. Do not exceed this range or you will damage the meter and/or yourself in the process of doing so. Certain levels require appropriate levels of PPE or personal protective equipment to measure them safely. Placement. This is the single most important step. One must put the DMM in the correct place to take the measurement of interest. Put it in any other place than the proper place, you won't be able to take the measurement you desire, or you'll damage the meter, your circuit, or yourself. Remember, ohm meters are never used on live circuits. They read the resistance from terminal to terminal with the device of interest removed from the circuit. Voltmeters, in contrast, read voltage across something. Voltage is a 2-point measurement. Finally, ammeters read current through something. Current is a single-point measurement which must flow in an indoor and outdoor. Your circuit may be completely functional, but you might be measuring it improperly. Improper use of a DMM might not just result in bad measurements, you might damage the meter, your circuit, or yourself. Finally, if you are absolutely certain your circuit is functional and it's still not conforming to your expectations and calculations, reanalyze your expectations and calculations. That's science, dudes. At any moment, I am prepared to abandon long-held convictions because rigorous and proven observations have demonstrated otherwise. Mankind no longer believes angry gods are the cause of thunder and disease because it's been scientifically proven that thunder and disease are caused by ghosts and aliens. Look it up. This is not to say that your circuit will ever disprove Ohm's law. I've yet to witness a lab group do this. I have, however, on numerous occasions observed students using something I call Mohs law, the opposite of Ohm's law. If your observations aren't jiving with your numbers and all else has failed, check your numbers. You might be using them wrong. Finally, trust no one. Verify. There will come a time when you are working on circuits and systems that have the potential to injure or kill you. Your life is on the line. Check to make sure all sources of hazardous energy are locked out and tagged out prior to initiating work. Bad habits are hard to break. Start safe work practices now. Okay, that about wraps it up for this introduction to Ohm's Law lecture. Here's one last visual on Ohm's Law that I never grow tired of showing students. I think this should be a mandatory poster in every lab environment. It goes well accompanying a kitten clutching a branch saying, "Hang in there, buddy." In conclusion, this lecture took a close look at the most fundamental of all electrical relationships known as Ohm's Law. We learned the cause, effect, and opposition relationship between voltage, current, and resistance, and used it to calculate unknown quantities given known or observed inputs. Additionally, we had a general introduction on troubleshooting basic electrical circuits using Ohm's Law. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.